You're welcome. Our previous lesson, we ended with this particular calculation of retardation. We had a body moving with a velocity of 80 meters per second, changing to 60 meters per second, 2 seconds, and we requested to find the retardation, which is of course very simple. For that matter, we said deceleration is equal to negative into v minus u divided by t, where the initial velocity u is equal to 80 meters per second, final velocity v is equal to 60 meters per second, and time taken is 2 seconds. When we substituted, we had it as negative 60 minus 8 in bracket divided by 2, which gave us negative into negative 20 over 2. And eventually that is positive 20 out of 2 and gives us a positive 10 meters per second squared. By the way, when you are writing retardation, of course, it means our answer is meant to be positive according to the expression. Remember, retardation is a negative acceleration, and acceleration is known to be v minus u divided by t. We agree that when we meet today, we are to look at the equations of uniformly accelerated motion. So let's kick on to that. Equations of uniformly accelerated motion. Equations of uniformly accelerated motion. Now here we say consider a body. Starting it is motion with an initial velocity u, and accelerates uniformly at a rate of a meters per second squared. I would like to be forgiven on this part here. We're supposed to include the unit of initial velocity. Please, you can put that unit, meters per second. It's missing there. So, and accelerates uniformly at a rate of a meters per second squared. Remember, that is actually the unit, the symbol used for acceleration, small a. So accelerates uniformly at a rate of that to acquire a final velocity v, that is small v, meters per second. Of course, sometimes you find in other books they use capital V, but at least small v would be better because capital V is an indication of very many terms in physics. For example, voltage in electricity. So wouldn't want to confuse, though of course at that moment when you're in motion it wouldn't represent voltage. To avoid confusion, we normally use small v, but if they use capital V, still you need to understand that symbol as per the topic. So to acquire a final velocity of v meters per second in time t seconds and covers a displacement of AC meters. You recall the time when I told you that our displacement, we shall always use S, and this is the point. Now, as shown below. In this particular subtopic, we zero ourselves to using vector quantities because there is a involvement of change in the direction. Though at some point, of course, using these very equations of motion, we shall determine or we shall calculate the distance covered. So we are going to involve ourselves in calculating the distance covered as well as the displacement of the body. Therefore, in this case, if we are to be on a safe side, we derive these expressions. So we put down these expressions using the vector quantities in linear motion. Now, this is our diagram. We have the body is somewhere here. So it's going to move along that road. It starts off, or you start observing it when it's moving at a speed of u meters per second, and then it travels a certain distance up to this point. So we do imagine you can measure the distance from the last end of that body up to the other last end, or from the middle to the middle. This is S meters. And of course, at this last point of observation, you see it moving at a velocity, final velocity of v meters per second. Remember, the acceleration of this body is a meters per second squared. That's our object moving along a straight road, along a straight line. Could be maybe a car moving on a road, straight road. So this is what we have. U, the initial velocity, v, the final velocity, s, the distance covered, the displacement covered. Of course, it can also be the distance covered, but of course we said we have to zero ourselves to vector quantities, and then a, the acceleration of the body according to the statement. Good. Now, this helps us now to derive the first equation of linear motion. First equation of linear motion. How do we come up with it? First equation of linear motion. Let's check it properly. The first equation comes from the definition of acceleration. What we said, we say from definition of acceleration, comma, what did we say? Mathematically, acceleration A is equal to final velocity minus initial velocity divided by time taken for change. Time taken for change. Remember, final velocity is v, initial velocity is u, time taken for change is t, according to our statement. So this would mean you have a is equal to v minus u divided by t. Don't forget to put the parameters that are subtracted into brackets, such that you'll be on a safe side. Now the next step will be to multiply both sides by t. So this would mean okay, we are saying multiply both sides by t. This would mean you have now t, okay, small a, this one here, multiply by t, this t is equal to v minus u, well, divide by t, then multiply by that very t. Mathematically, you can realize that this t and that t will cancel out. So on the left hand side, you shall have at. On the right hand side, you shall have v minus u. Now we are going to make v the subject of the formula. So this would mean you have at plus u is equal to v. And eventually, we have the expression as v is equal to this u plus that at, and that gives us the first equation of linear motion. So here, what does that mean? It means that if you have the initial velocity, you have acceleration, and you have time taken, you can get the final velocity. As well, if you have the final velocity, you have the initial velocity and acceleration, you can get the time taken. Or if you have the final velocity, initial velocity, and time, you can get acceleration. And finally, if you have the final velocity, you have the acceleration, and the time, you can get the initial velocity. With the time, we shall see how this expression is applied in numerical questions. Let's continue. We go to the second equation of linear motion. Second equation of uniformly accelerated motion, in simple terms, of linear motion, but we say the equation of uniformly accelerated motion. Here, where do we start from in deriving this expression? We start from the mathematical treatment of displacement. The mathematical treatment of displacement. What do we know about displacement, by the way? Displacement is given as average velocity times time. Average velocity times time. So what is the average velocity? Now remember that we said our displacement will be represented using letter S. So we zero to the symbols. What about the average velocity? I recall very well at the beginning of this topic, we had a term called average velocity. Defined it and put down the mathematical expression of average velocity, and that was v plus u divided by 2, or you can simply say u plus v divided by 2, then times time. This time here, this average velocity is this final velocity plus initial velocity divided by the way, it's like a mean velocity. Remember, when you are given the data and they ask you to get the mean, you get the sum of all the outcomes divided by the number of the outcomes. So here, the outcomes we have is the final velocity and initial velocity. And the number of items or the number of outcomes are 2, because we're talking about only final velocity and initial velocity. So we say final velocity plus initial velocity divided by time gives us average velocity. Then we multiply it by time. Now, this means that if I multiply throughout by 2, multiply throughout by 2, it would mean we have 2 times S is equal to V plus U divided by 2 times T again times 2. Yes. Now, our mathematics students, you know very well that these 2 and these 2 will cancel out. And eventually, that would mean that on the left hand side we have 2s. On the right hand side, since 2 has cancelled out. We have v plus u then times t. Okay, can we open can we replace that v? Let us replace that v here. Okay, we can first open the brackets. When we open the bracket, we shall have 2s is equal to vt plus ut. Okay, but remember, from the first equation of motion, v is equal to u plus at. V is equal to u plus at. So can we replace this expression here into this very thing here? Can we place it where there is a v? Where there is a v, we can put that. So when we replace it, we shall have 2s is equal to u plus at into bracket times t, then plus ut. Very good. Can we open the bracket now? When we open the bracket, we have 2s is equal to ut plus at squared, then plus ut. Now we are going to collect the like terms. We have 2s is equal to 2ut plus 8 squared. Now next we are going to divide it through, because we want to make s the subject of the formula here. We are going to divide it throughout by 2. So divide through by 2. That would mean you have 2s divided by 2 is equal to ut divided by 2 plus 8 squared divided by 2. And eventually you will have s is equal to ut, that one there, because the 2 cancels out, plus a half at squared. So this is called the second equation of uniformly accelerated linear motion. Now in this expression, it means you can get the displacement of the object when you know the initial velocity, you know the acceleration, and you know the time taken. Or you can get the initial velocity if you know the time taken, and you know the displacement and the acceleration of the object. You can as well get the time when you know the initial velocity, you know the final velocity, and you know the displacement. And there is something to watch out here. If you know the initial velocity and is not equal to 0, and you know the acceleration and you know the displacement, you will come up with a quadratic equation. Those who have been doing mathematics, you know the quadratic equation, how they look like. It will be a quadratic equation in terms of t, implying that you are going to involve yourself in calculating 2 values of t. And we have to be very careful. One value will be negative, another one will be positive. So far, we have not seen an incidence where we calculate time to be a negative. So you will have to take a positive answer as the time taken. So you have to be careful there. Okay, so let's push ourselves to the third and the final equation of uniformly accelerated linear motion. Third equation of linear motion, or simply uniformly accelerated linear motion. We can also still get it from displacement. We can still get it from displacement. So we shall still say that displacement is equal to average velocity times time taken to cover that displacement. Remember average velocity because the body keeps on changing, reducing, increasing. So we have to use what we call average velocity and the total time taken. So this means we are going to have S is equal to V. Okay, we can start with U. Some people are complaining. u plus v divided by 2 times t, the time taken. This time around, we shall say that from v is equal to u plus at. By the way, when you look at it properly, your t will be the same as v minus u divided by a. Mathematics, that is simple mathematics. By the way, look here, you see this u, when it crosses the equal sign, it becomes a minus, so you'll have v minus u, but on the right hand side you'll have remained with the at. So to make it the subject of the formula, you'll have to divide it throughout by a. Remember, on the left you have v minus u, on the right you have at. So a on the right will cancel out to leave you with it alone. Then on the left hand side you have v minus u divided by a. But of course, we are making it the subject of the formula. It has to be on the left hand side, and the rest will go to the right hand side. Now we are going to substitute this every expression for t. We place it in the previous expression for average, for displacement. If we did that, then that would mean we have s. We have s is equal to what? S is going to be u plus v divided by 2, then times v minus u divided by a. Let me go to another page. Now, recall the multiplication of fractions. So this would mean that s, which is on the left hand side, will be equal to v, u, because we wrote u, plus v times v minus u all over 2a. Remember, this one we had v plus, u plus v divided by 2. Then this one we had v minus u divided by a. And we multiplied the two fractions. So the numerators are multiplied together, and the denominators also multiplied together. Let me now multiply throughout by 2a. Multiply through by 2a. So what does that mean? We shall have 2a times s is equal to u plus v into v minus u divided by twice a, then multiply by 2a. Mathematical again, the 2a on the right hand side will cancel out. We shall remain with the 2as is equal to u plus v minus u. Now that is a factorized expression. We are going to expand the right hand side. So if we are to expand, it means every term of the first bracket must be multiplied by the second bracket. So this would be u, that one, into, you multiply by the second bracket, then this is a plus v, so plus v again into v minus u. Can we open the bracket? Yes. This is uv. Remember, this is positive u times negative u. It gives you minus u squared. Then this is v squared. So it is plus v squared. This is a plus v times a minus u. So it is minus uv. This is very simple. Do you see this term here? Let me circle it properly. You see this term here? It is minus uv. Do you see this term here? Is plus uv. Now these two, when they are added, they give you 0. So if that is the case, then it implies that actually we are saying that our 2as, which is on the left hand side, is eventually equal to minus u squared plus v squared. So let us make v squared the subject of the formula. So this would mean let this cross the equal sign. When it comes to the left hand side, it becomes a plus u squared, then plus 2as is equal to v squared. And now eventually we shall say that v squared is equal to u squared plus 2as. s. So this is called the third equation of uniformly accelerated linear motion. Now here you can get any of the parameters if you know the rest. For example, you can get v, that's the final velocity. If you know the initial velocity, you know the acceleration of the body, and then the displacement. Or you can get the initial velocity if you know the final velocity, you know the acceleration, and the displacement. You can as well get the acceleration if you know the displacement, you know the initial velocity, and you also know the final velocity. Or else you can get the displacement if you know the acceleration, you know the initial velocity, and you know the final velocity. This too is a constant, so it will remain there. By the way, at times you may find yourself in a particular question applying almost all the equations, or two equations, or simply one equation. Depends on the question that has been set by the examiner. So members, for today, let us stop here. Next time when we meet, we shall start from there, possibly to look at how we can apply the equations of uniformly accelerated motion in calculating or in solving numerical equations in linear motion. Thank you so much for your cooperation today. Bye bye. We'll meet next time.